Alrighty, in this video, we are going to be talking about sequences. And hopefully you guys remember your Math 1 and Pre-Calc skills because I'm not going to reteach you guys sequences. Hopefully you guys know what an arithmetic sequence is and what a geometric sequence is. But what we are going to do, however, is talk about what happens as we approach the infinite term in this case. So a sequence has limit L, written as the limit as n approaches infinity of a sub n, aka my sequence, is equal to L. Now, if it has a limit, then it converges. If it doesn't, then it diverges. Here are some properties that you should know by now, and what we're going to do is just go ahead and do these problems. For number one, we want to determine whether each sequence converges or diverges, and if it converges, then we are going to determine the value. So essentially here, as I approach infinity, what happens? Now back in AB, especially back in August in Unit 1, we talked about how if we have the same degree, we could look at our coefficients. So we're going to use the same strategy. In this case, this tells me that my limit is 2. So this means that my sequence will converge to 2. So for example, if I have my first term, that's going to be 2 minus 1 or 1, so 1. If I have my second term, 4, 3 over 2. If I have my third term, 5 over 3. If I have my fourth term, 7 over 4. And if you were to continue on, you'll see that it's going to approach 2. Now for number 3, as I look at cosine of n over 2, you'll notice that this will oscillate. Because it oscillates, this tells me that my sequence would diverge, because we don't necessarily know what the sequence will eventually stop at. Now remember that we can't really say does not exist because this is in terms of a sequence and not a function. So the correct terminology here would be divergent. Okay, for number 6, we're going to do the same thing. All right, if I were to plug in infinity here, I have 1 over some really big number, which is going to be 0. So now I have 1 to the nth power. And if n is approaching infinity, now I have 1 to infinity, which means that I have indeterminate form of 1 to the infinite, 1 to infinity. Because I have indeterminate form, I should probably figure out a way in which we have to use L'Hopital's. Because we have a variable as an exponent, one logical way is probably thinking about logarithmic differentiation and take the ln of both sides, which I'm going to do here. So here I'm going to take the ln of both sides. And while I take the ln of both sides, I'm also going to bring down the n using my log rules to get that lovely thing right here. Of course, I have to include limit. All right, so now I'm going to reevaluate this and see if I can use L'Hopital's. I have infinity, and then I have ln of 1 plus some really big number, aka 0. ln of 1 is 0, so now I have 0 times infinity, which still I can't use L'Hopital's just yet, because I don't have infinity over infinity, and I don't have 0 over 0. So once again, I'm going to finesse my way into making it so that it looks like 0 over 0 or infinity over infinity. All right, so now I have ln of 1 plus 1 over n and 1 over n. In this case, we know that if I were to plug in infinity here and here, this is going to be 0 over 0, which means I have indeterminate form, which means I can finally use L'Hopital's. Now, if this was an FRQ, you need to make sure that you actually write out the numerator and the denominator right here, which I didn't do. But for good practice, you want to make sure that you do that because you don't know what that FRQ is going to look like. All right, once I take the derivative of this lovely thing right here, you'll see that I have -1 over n squared and -1 over n squared, which cancels out. So now I just only have this lovely thing. If I were to plug in infinity here, this is going to be 1 over some really big number. So that's going to be 0. So 1 over 1 plus 0, or 1 over 1, which is just 1. So the right side is just 1. Remember that I'm solving for y because remember that y is technically this limit right here, which I initially wanted. So I'm going to log both sides to get y, which means that this sequence right here will approach e. All right, number 7 right here. Don't multiply this out because it's going to be nasty. Remember that one of the rules is using the product rule in terms of limits, where I could take the limit of the products. So here, I'm just going to take the limit of this and take the limit of this. Of course, you do want to make sure that you actually write it out. And then see what happens in the long run. This case, I'm going to use my same degree because this is 1 and this is 1, which means that this will approach 1/2. This sequence will approach 1/2. And then this sequence right here will approach 1 because we already know that 1 over n, 1 over some really big number is going to be 0. So 1 minus 0 is 0. The sequence of 1/2 times the sequence of 1 will converge to 1/2. All right, now same thing with number 8 here. For number 8, I don't really know what to do with n squared and 2n minus 1, but what I do know is that we could use relative growth rates for this one. Here I have n squared, and then here I have 2 to the n. You want to think what's bigger, n squared or 2 to the n? You'll know that 2 to the n is bigger because 2 to the n is bigger and it's at the bottom. We will know that this will eventually converge to 0. Now, can you use L'Hopital's for this? Technically, you can because this is going to be infinity over infinity, which means I'm going to have 2n, and then I'm going to have, if I were to take the derivative of that, I'm going to have ln of 2 times 2 to the n. All right, and then eventually this will keep on repeating itself. This isn't going to be a pretty number because it's going to keep on repeating itself. We eventually have to use relative growth rate for this. Well, then again, if I were to do 2 to this really big number right here, well, first, I'm going to use L'Hopital's again. So 2, and then ln of 2. Times ln of 2 times 2 to the n. And then you could see that 2 to some really big number is going to be a really big number, which is going to be 0. I mean, yeah, some really big number. So I have 2 over some really big number, which means that's going to converge to 0. Number 9. Same process. So think about what can I use for this one. In this case, I have ln of n and n. This is going to be infinity, and this is going to be infinity. So I'm going to rewrite this. Because remember, we don't know what's going to be on the FRQ, and we want full points. This is an indeterminate form of infinity over infinity, which means that we could use L'Hopital's. Then, of course, I have 1 over n on top and 1 at the bottom. The limit as n approaches infinity of 1 over n will approach 0, which means that this sequence right here will converge to 0. Number 10 is an easy one because you know that we have -5 n to the fourth and n to the fourth. So looking at my degrees here, I'm going to take the coefficient, which means I have -5 over 1 or just -5. All right. Next part is talking about the absolute value theorem for sequences. Essentially, if I were to take the limit of the sequence, the absolute value of the sequence, and if it approaches 0, then the limit is 0. If it approaches something else, then it is going to diverge. Now, the reason why is because if we have something like this, and we have -1 to the n and n, you might have something like this right here, where it will converge to, in this case, 0. If you have some other number, though, let's say -1 or -2, let's say that 1's up here and -1's right here, then it might look something like this. And that's not going to be pretty because, of course, we don't know if it's going to converge to 1 or we don't know if it's going to converge to -1. So that's why it's important for us to see if it approaches 0, because if it does, then it converges to 0. If it doesn't, sucks for us, it diverges. All right, so let's see number 12. I am going to take the limit of the absolute value of a sub n, and that is going to be the same thing as saying 1 to the n, or just 1, and n plus 1 over n. If I were to look at this limit here, I have the same degree. In this case, I'm going to look at my coefficient. 1 over 1 is just 1. Now, because I have this right here, this tells me that my sequence is going to fluctuate from -1 and 1, and I don't want that. Because it's going to fluctuate, we don't really know where it's going to converge to, which means that number 12 is divergent. For number 12, if you want to look it up on Desmos and graph this, you can, and see why it is divergent. Number 14, the limit as n approaches infinity of a sub n, the absolute value of a sub n. That's going to be the same thing as 1 plus 1 to the n, or just 1, and then n squared, which is going to be 2 over n squared. And we know that that will approach 0. Since it's equal to 0, we know that this right here converges to 0. For number 16 right here, we have n minus 2 factorial over n factorial. As a reminder on what n factorial looks like, if I were to have 6 right here, 6 factorial, this would be 6 times 5 times 4 times 3 times 2 times 1. So if I were to think about n factorial, then this is going to be saying n minus 1, n minus 2, n minus 3, n minus 4, and so forth. If I have n minus 2 factorial, that's going to be very similar, but we start at n minus 2. Oops, that should be 3. N minus 2, n minus 3, n minus 4, n minus 5, and so forth. You will see that stuff will easily cancel out, so n minus 3, n minus 2, n minus 4. Eventually, the n minus 5 will cancel out, and everything else will cancel out, which means that I'm left with 1 over n minus 1 for my limit. And that is going to approach 0, which means that this will converge to 0. 18 is another problem where we have to use relative growth rate. You see that a factorial will always be greater than anything else in terms of exponential. Because the factorial will always grow faster, this tells me that the sequence right here will be divergent. So factorial is always bigger. All right. In the next video, we are going to be talking about series, and hopefully you guys remember your pre-calc skills back and series.